Hello everyone, my name is Viraj and welcome to the post-contest discussion for Leetcode Weekly 439. Today we'll be discussing the problems from this contest. Before we begin, let us discuss a little about version 2 of CP31 sheet by TLE Eliminators. For all those who are not aware, this is a sheet of 31 CP problems, all from the range of 800 to 1900 with interesting and reusable concepts and ideas. So a perfect sheet for all those beginners and amateur people who are trying to advance in their journey for competitive programming. Our version 2 has definitely an advanced UI, maintains a leaderboard for you, progress board for you, and has newer problem set from 1700 onwards as compared to the last sheet. So do check this out, and I think this is one of the best sheets you can find there so that you're able to boost all that is needed in your CP journey. Okay, so that is all. Let us quickly move on to the first problem. Find the largest almost missing number. So a relatively easier problem. As you can say, a target is tag is also given as easy. We can also understand that this is the first problem in Leetcode, so this happens. And the implementation over here is just going to be a point of issue if you are a beginner. Otherwise, I think you might be able to understand what do we want. So you are given an integer array nums and an integer k. An integer x is almost missing from nums if x appears in exactly one subarray of k within nums. Return the largest almost missing integer from nums. If no such integer exists, returns a -1. Now a subarray is a continuous sequence of elements within an array. Great, so let us quickly generalize this problem. They are saying that there is an array, let's say, and the numbers are a1, a2, a3, a4, a5, a6, so on till, let's say, an. Now there's a variable k. What are they saying is, you go to check every k-sized subarray. So let's say k over here is 3. So I'll say, okay, a1 to a3, this is a subarray, right? Continuous elements 3 picked up. a2 to a4, another subarray. Let's say then a3 to a5, this is another subarray. Then a4 to a6, another subarray. So every 3 size subarray you pick up. In that 3 size subarray, you basically see that which elements are coming. And after you actually see them, you can note them down somewhere. And then the answer that we want to print actually is, when I have all this information with me, I want to print the largest element which comes in k-sized subarray exactly once. This is my main question. For example, let's go back and let's say see this test case. I think this is going to be better. 397217. 397217. Let's see this. So you have the array as 397217. Now in this case, k is equal to 4. So can you think about all the 4 size subarrays that we have? Yes. So this is like a 3972. This is one. Then 9721. This is one. And then 7217, this is another. So if I talk about the first subarray, I'll name this. This is like 1, this is 2, this is 3. So for the first subarray that you have the elements 3, 9, 7, 2 coming in that. So I can say that 3 is falling at least in one subarray now, right? 9 is falling in 1, 7 is falling in 1, and 2 is falling in 1. If I talk about the second subarray now, we can try to update the values. 9721 comes. So 9 now falls in 2 subarrays. So you can update this 9. You can say this is 2. 7 comes in 2 subarrays now. So this is 2. 2 comes again in the subarray. So this is 2. And then 1 is now new. So 1 can be marked off with 1. The next time when I talk about the third subarray, 7217. Now 7 comes once in this subarray. So I can say, okay, 7 has now coming in 3 subarrays. So this updates to 3. Then 2 comes, so 2 now updates to 3 because 2 now is visible in 3 subarrays. 1 is now visible in 2 subarrays. And now this can be a small confusion point. I am taking 7 once more. So for all the beginners who might not have understood the question initially, you don't have to say 7 is coming again, so you mark this off as 4. No. Remember, we are just talking about a number coming in that subarray. Now, if in the third subarray, 7 comes 2 times, so I'm not going to count 2 occurrences. I'm just saying 7 comes in this subarray. Okay, fine. Let's count its occurrence of coming in a subarray. So now if 7 comes again, I'll still keep this as 3 because 7 is visible in 3 subarrays. Inside a subarray, if it's visible more than 1 times, that is not something I want to mark with. It's just that it should be there in that subarray. I hope this part should be clear. Okay, and now when I have all this data, I can just update it out. So this data finally turns out as something like you have 1, you have 2, you have 3, you have 3, and you have 2. Okay, I can rub everything else out. And now when I have this new based data with me, then what do I finally observe? All the elements which basically have 1 next to them, they indicate that they are coming exactly once in all the subarrays that I created of k size. Now, if I pick up 9, this is not right. It comes in 2. 7 comes 3 times, 2 comes 3 times, 1 is coming 2 times. That means the only guy left over here is actually 3. So you will say that 3 is your answer. Okay, 3 is your answer. Now, remember the question is largest guy. For example, had there been 9 also, which comes only in one subarray, then you would have actually compared 3 and 9 and you would have said, now the answer has now turned out to 9. Okay, because you had 2 options to take from and 9 is the larger guy. So in that dependency, you know you have to maintain some sort of a max variable also to figure out the largest guy possible. Okay, I hope this part is clear. I hope the question is clear. Now, if I go back in the question, we can see that the constraints are very, very low. Okay, size is 50, numbers are also into 50, and then k is also in that 50 order only. So a very naive solution which can come to your mind is, if I'm talking about each and every subarray, why don't I actually go to each and every subarray and just do what I was required to do? Meaning, how about you actually go to every subarray, let's say went to the first subarray, went to the second subarray, went to the third subarray, and this data that I just produced in front of you, you produce this back by coding. You can be like, okay, somehow when I finally figure out my piece of structure, my piece of code, I end up with 3 being 1, and I think I'd updated this. So 9 becomes 2, and 7 is 3, 2 is 3, 1 is 2. So I get all this mapping that is there, which shows that, okay, what are the occurrences that I was talking about, occurrences in each and every subarray that I was talking about. And when I actually have this mapping, all I would want is just run a loop on this mapping. Whichever has a frequency 1, that guy is a potential answer. Let's max out all those potential answers. Okay, so what would be our pseudocode structure? Pseudocode structure would something be like, I'll write an argument over here. We will try to go to every subarray, then in that array, figure out unique elements. Why did I say unique elements? Because we just saw this over here. If I talk about this 7, like in this third subarray over here, this third subarray has 7 coming 2 times. But did you consider 7 2 times as an overall occurrences? Remember, this is not a frequency something that you're marking off. You're basically marking any one occurrence because you know 7 comes in the third subarray. So that means if this subarray is something I'm talking about, I'm looking for the unique elements in this. I'm looking for just 7, 2 and 1, not 7, 2, 1 and 7 again. So I can say that in that subarray, I'll figure out the unique elements, and then in some global map, you can say global map, we push their occurrences from the unique structure wherever you store that. Okay, unique or uniques structure where I store. Okay, and this is going to be my overall algorithm. When I complete this algorithm, when I go to every subarray somehow and I have that uniqueness, unique elements in that subarray, I try to push them inside a map. When I do that, I know at the very end of my whole code logic, I end up getting this mapping that I want. And then the answer is straightforward. Just run a loop on this map and get all those guys which have one frequency, print the best or the largest guy out of those. Okay, this is my overall logic. So now all that would left to do is discuss implementation. Now this has small subparts that we're talking about. So those parts should be clear. You're basically trying to figure out every subarray. That is one case. Then you need something for you storing the unique elements and then some global map. So for this knowledge, basically you should understand how do we actually get to every subarray, and how do we set and store these unique elements, and how do we get them in the global map. So this part and this part is pretty much clear. Like to store the unique elements, you can of course use a set or an unordered set, whatever you want to save time complexity in that scenario. A global map is also common. You can just declare it somewhere above the logic where you start with. But how do we go to every subarray? So just for the beginners out there, I'll quickly discuss a rough idea for this. Basically, we start off by saying there is a for loop outside, and this outer for loop controls, let's say, an I pointer from 0. And this I pointer indicates the start of every subarray. So if you have, let's say, these many 3 subarrays, let's say you're trying to take, then basically I is pointing to this first, then this first, then this first. And then you can say that if that is the case, I want to make I go to a certain limit. I don't want to make I go to less than equal to n. No, that is not the case. I want to make it go to, if I am talking about k size subarrays, I should be less than equal to n minus k, right? Example, let's say n over here is 5 and let's say k over here was 3, for example. So 0, 1, 2, 3, 4, these are the indexes. Basically, you want positions at 0, 1 and 2, and then 3 and 4 are not considered, because if you start with 0, this is a subarray of 3 size, this is a subarray of 3 size, this is a subarray of 3 size. So how do you get this I last 2 to iterate till? 5 minus 3, that is 2, so you can want to go till 2. So hence this whole brute force idea. Okay, so and then we do something like an I++. Then inside this, I need another for loop. This is another pointer which basically makes me iterate in every subarray. Now every subarray has a length k. So I would want that if, let's say, this is a subpointer j which starts at the I location, j should be less than I plus k, and then I write j++. And this is like a brute idea, brute solution, where we actually are able to get to every subarray. Now when we are inside every subarray, we first want to figure out the uniqueness at this location, that is the inner loop. And then outside this inner loop, basically you can say, I want to insert all those elements in some map. This is the brute structure. I hope this part makes sense. Let us quickly jump to our code part and see how do we implement this out. As we go along the code, I think you will actually understand what I mean over here. Okay. So this is my code structure. Now there can be multiple ways to implement what I just said. It's just that the brute idea you want to remain same, because there's a lot of time complexity that is allowed over here. So even a very larger complexity than what I propose would be fine. Okay. Now you have n equals to num size that I declared. Then I have these map occurrences that I want. I created a simple map int comma int type. I run this brute logic of going into every subarray. I equals to 0, I less than equal to n minus k I++, and then I have an unordered set. This is int type unique, and then I have going every subarray's number, insert that number in that set, after which I know I just want to iterate in that set and make all those numbers ++ in my map. So this basically makes sure that in every subarray, whichever numbers did pop up, their mapping gets increased by 1. And when I end this whole logic, I know that I have a very neat map with me where every number has an equivalent value, and that value indicates how many subarrays did that number come into. And now I want that largest missing guy. I can declare this -1. Why -1? They also give you a base case that if, let's say, there is no largest almost missing number, you return a -1. So I can start with -1 and I can max this number out. I can say if in my occurrences map, if it.second, that is the frequency, is 1, then I know I want to max this guy out with it.first, that is actually the key or the element's value. Okay, and then I get the answer and I return this. So if this remains -1, that's fine. If it gets updated by some other larger guy, I return that piece. Okay, now this of course runs on all these cases over here, and I hope this should make sense. Now what is our time complexity in this solution? I am using an unordered set over here, so that is pretty much giving you constant time complexity of maintenance. What you can do is you can have this insertion over here, so this is pretty much constant. You can have this above loop, that is n order. This loop is also actually like an n order over here. Then this is, because I've used a normal map, so you can say this is like a log n order extra. Then this is pretty much n order roughly, and this is pretty much log n to extract and do stuff. So I can say I'm getting a solution that's pretty much n square only. So you have like the time complexity over here would be written like this. You have time complexity as n into, then you have n plus log n inside that. Okay, and then plus outside, this is n log n. So now in this n into n plus n log n plus n log n, so n log n characters can be ignored because n square is larger in that, so you can write simply as n square, which is like 50 square. If I write 50 square, is that fine? Yes, that is fine. And 50 square of course works as expected, easier problem, so this is very low. And then what about the other time complexity, space complexity that we talk about? We have this set, we have the map, that is maximum 50 order I think we should take, because maximum we are storing 50 numbers in this. Okay, I hope this is clear, and this is all that is there in this first problem. Let us quickly jump to our second problem. Okay, so longest palindromic subsequence after at most k operations. I mean, the question name is pretty easy to judge what must they be asking. You are given a string s and an integer k. In one operation, you can replace the character at any position with the next or the previous letter in the alphabet, wrapping around as you do so. So this is very important. We'll discuss what does that mean. For example, replacing A with the next letter results in B. Replacing A with the previous letter results in also Z. Similarly, replacing Z with the next letter results in A. Replacing Z with the previous letter results in Y. Now, you have to return the length of the longest palindromic subsequence of S that can be obtained by performing at most k operations. A subsequence is a non-empty string that can be derived from other string by deleting some or no characters without changing the order. And palindrome is, I think, very, very easy. It reads same from forward and backward. So I think every term in this should be very, very clear. You can give it 2 minutes thought. Let us generalize this problem. What are they saying is they'll give you a string S, okay? And that is the letter S1, S2, S3, S4, S5, S6 on till Sn. Now everything is small lettered, so the letters belong from small a to small z. Now they have given you a variable k over here also. What are you trying to figure out? You're trying to figure out that you basically end up creating the largest subsequence from this particular string, which is palindromic in nature. Subsequence means you can delete letters from anywhere that you want, and when you collect back the string, it should have the same order. So that means, let's say I pick up S1, then I pick up, let's say S4, S5, S6, then let's say Sn. So this is a subsequence. S1, S4, S5, S6, Sn combined or concatenated together is a subsequence that I have picked up from this string. So I think subsequence should be clear, very beginner friendly stuff. Now when I want to do this, when I want to create the largest palindromic subsequence, I have been given, you can say, availability of this k value that is representing what? This k is basically an upper limit on the operation that I can perform. What operation can I perform? If I have any letter si, for example, I can make this letter go from, in the English alphabet, its previous letter or its next letter. And this is considered one operation. So for example, let's say I have A. I can take A to B. If I have B, I can take B to C. I have C, I can take C to D. So this is going forward. Or if I had A, I can also make A to its previous letter. Now in the English alphabet, there is nothing before A. That is why they have actually given you a small indication that we are looking for a rotated cycle in this. Means from A to the letters when they extend to Z, basically if A's previous is asked, you don't say, oh, there is nothing to A's previous. You say, okay, A has a previous back to Z. This is very important. Similarly, if I tell you that which is the character on the next of Z, Z has actually nothing next to it, but technically because this is like a rounded shape, you can say Z's next character is actually back on A. So this is the cyclic nature of alphabets that normally pop up in questions like strings. So this should be very, very clear with you. And I can promise you this concept actually gets implemented a lot of different places where they talk about cyclic nature in the English alphabets. So now the power is, as I repeat, what is the power? I think I should not rub this. What is the power? The power is if you are at S of I or whatever that letter is, or let's say a character CH, you can go to the next guy or you can go to the previous guy. Okay, now this is considered as one operation. What is K now? K is telling you that you can perform at most K operations. So if let's say you have performed OP number of operations, OP should be less than equal to K. No more than K operations is allowed. When you perform these operations on any number that you want, any character that you want, you perform this on S3, maybe you perform this on Sn, maybe you perform this on S5. However you want to do this and tell me what is that largest palindromic subsequence that I can create. To be very specific, they're not even asking you that particular string or subsequence that you want to print. They just want that length of that subsequence that is there. Okay, so this is the whole question. Let us look at the test cases and understand what do I want from this. So for example, the first case A, B, C, E, D. So you have A, B, C, E, D, and then K is equal to 2. So now over here, I have, let's say I can do one thing. I can change this letter B to its next letter that is C, and this letter D to its previous letter that is C again. Now the string is ACCEC. Now let me pick up CCC, and this creates CCC, which is of course a palindrome. It's basically the same string all around, no different character, and this has a value of 3, basically size of, you can say, 3. So 3 becomes my answer. I can do no better than 3. By the way, just to give you another piece of set over here, it's never written because that which string are you trying to actually make of 3 size. Maybe there are multiple answers, and I'll show you why. If I talk about A, B, C, E, D, how about I would have made A to its next letter B and C to its previous letter B. Now you have B, 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 E, D. In this also there is B, 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 which can be collected and can be said this is a palindrome and this has a length 3. Okay, so were you bothered with actually the length or were you bothered with the string? You're actually bothered more with the length. That means there is a possibility of multiple answers, and this is a good idea to start off with. Okay, I hope this test case is clear. Let's quickly discuss the other test case also, and then we'll begin with our idea. A, Z, 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 K equals to 4. So you have A, and then Z, Z, Z. Now K is 4. I'll give you an answer for my own. I can make this Z go to A, this Z go to A, and this Z go to A. Now if this happens, what is the length that I actually get? I get exactly a length 6, which has everything same, which is a palindrome. Now I have used 3 operations. So this is another important point, that remember, it was said you want at most K operations. It doesn't mean you have to use exactly 4 operations. In this case, you use 3 operations, fine. 3 is less than equal to 4, still good to go. I hope this part is clear. Okay, now the problem is clear, the test cases are clear. Let's actually jump to one very strong intuition over here. Look at the length of S and the K value that is given. This is very, very small. Both are in 200 order. Now this hints me that I can actually create solutions that look like S into K also. If I create something like S into K, that would be like 200 square. Even if you actually create something like S into K into, let's say, K again, for example, I'm just trying to get you an order of 200. Even if I create something, for example, the idea is if you create something that looks like 200 square, that is also fine. If you create something like 200 cube, by the way, this is also going to work because 200 cube is barely going to be what? This is like writing 8 into 10 power 6 order. Now, if you write 8 into 10 power 6 order, don't you think this is less than the normal limit of 10 power 8 operations? Right? You can perform an 8 into 10 raised to 6 order solution, right? Correct. I hope this part should be clear. And this whole idea of expected time complexity is also a very good indication that what sort of a solution can you go to a limit. And this becomes a very good starting point. If I can go to a 200 cube limit also, I can extend my, you can say, cushion, and I can try to make solutions that look in that order. Great. I hope this part is clear. So this is one intuition. The other intuition I already shared with you, that you don't exactly want the string, rather you just want the length, which means multiple answers are possible. So basically the next thing that comes to mind is you have a large enough, you can say, time complexity to explore. So you can write it like this, enough TC, something like that. And the second idea is you are only looking for length. That means there is a chance of multiple answers. Now, if there is a chance of multiple answers, that means there are various possibilities you are looking to explore, and where various possibilities come into picture, out of which you're looking for a best answer, solution like a DP based idea should come to your mind. Why DP based? Because DP indicates this part only, that I'll try to explore everything and I try to take the best out of that. I hope this creates a good intuition in your head, and let us move on to our main idea. Now, on top of this, I'll give you idea number 3 that also strikes when you look at this problem. You are looking for the third thing that is called a palindrome. Now, if a palindrome is tried to be created, palindrome basically reads same from forward and backward, which means you basically would want that from the back, if you have some I, and from the front, if you have some I, and from the back, if you have some J, you're trying to match I and J. If they match, that's great. If they don't match, maybe you do try to match them, or maybe you do try to skip them. Meaning, when I look for a DP based solution over here, as I said, I want multiple answers to explore, and I also want palindrome, this now indicates that I would look for a solution which creates a pointer based method. I would want that I have a pointer I that goes from the front. I want that I have a pointer J that comes from the back on this string S. So this can be like S1, S2, S3, so on till this is like Sn-2, Sn-1, Sn. So I want something to go from the front, something to go from the back. let's try to iteratively think what is going to happen. You are standing at S1, you are standing at Sn. Now think of the options that you have over here. You also are talking about a subsequence. Now a subsequence definitely gives you this power that it's not compulsory that you take every element that you want or every in this letter that you want. So one option can be, how about if Sn is the guy that I want to skip? It's not necessary, right? Maybe I say, okay, Sn is something I don't want even to become part of my subsequence. If that happens, I would just say that, okay, I would want to make my j jump to Sn minus 1, and then I will continue whatever I want to do, so forth and so on. So if let's say I have some sort of a function that does this for me, I think you are now understanding where does this dp come into picture. If you are thinking some sort of a function which passes this I, you can say like there can be a top function which has what is passed in this I, you can say j and then string s. And when all of this is passed, you can be like, okay, let's talk about creating my answer for had I actually taken, I think added to this, you will also work with k over here. That is the k operations, that's the k element that you want. So now what we can talk about is you can say, okay, if I have an option, I can maybe try to just skip j. So I can be like, okay, one answer comes from writing function of I, j, s, k, or in this case, this j turns out to be j minus 1. Because you just said, okay, the jth letter is something I don't even bother myself with. I don't want that to become part of my subsequence. The other thing can be, how about you do the same thing with I? You'll be like, okay, S1 is a guy I don't want. Let's make I jump to S2. So I can be like, okay, the next thing is I plus 1, j, s, and k. And what is the last thing that you want? The last thing is you actually want S1 to be part. You actually want Sn to be part also. Now, if you want S1 and Sn both to be part of your whole structure, you would ideally look for something known as how much operations do you actually want S1 and Sn to make equal to. Because it's not necessary S1 is equal to Sn, right? Is that necessary? If S1 and Sn become part of your subsequence, that means somewhere in your subsequence, S1 has to be equal to Sn, because your subsequence needs to be palindromic. So from the start, you are looking for two letters which pair up, which are same. So S1 needs to be equal to Sn. In that scenario, you of course want to first figure out what is S1 and Sn's operation count that comes up so that I know I make S1 equal to Sn. And to do that, we can have some sort of a caller helper function, you can say, outside whatever we are doing. This caller function is going to do our sole task to figure out if I pass some si in this and I pass some sj in this, how many operations do I use to make si and sj equal? By what sort of an operation we are talking about? Just moving either to the next letter or the previous letter. Okay, now let's just solve this portion quickly. Let's say si is b. Let's say sj is d. Tell me, what do you think is going to be the answer? Very simple. It's going to be 2. Why 2? Basically, if you talk about b over here, you can just increment b to c, then increment c to d. Now, you have this also d, this also d. Or you could have decremented d to c and decremented c to b. So you have this also b and this also b. So now from here you get the answer 2. Now I'll give you the other thing over here. For example, you are given a and z. What happens now? Do you think you want to make a go forward and take it to z? That would take, I think, like 25 operations. The other thing is, how about you make a go backward and this becomes z and this becomes z? So that takes 1 operation. So because of the cyclic nature that is there, either next or the previous element, you have to consider both directions. That means you need to figure out the difference between sj and si, considering sj is greater than equal to si. And then this is the difference which I can say si takes to make its way to sj in the next direction. Or if I want to figure out the previous guy, as in if I want to take a direction that's in opposite direction would say 26 minus this difference, that is sj minus si, actually gives me that particular value. Which means si and sj together will give 2 possibilities. You can figure out what is the absolute value. Just to keep it simpler, don't want sj greater than si always. Let's say si is greater. Just take the absolute because it's just the difference between them. Let's take the difference between their ASCII values in that case. So si minus sj, when I'll write quickly, I'll get their difference in their ASCII values. Now this difference is going to be one part of the difference. As in, if it's talking about the next guy's jumping or the previous guy's jumping. I want the other part also. The other part is, if let's say this is the difference D, or let's say D1, the other difference D2 is actually 26 minus D1. Because then this would mean what is the other direction you could have taken and how much iterations did you want it there, or how much operations did you want it there. And then what is actually your answer? Minimum of D1 and D2 gives you the answer. So if you want to take the next direction path, you get the answer from there. If you want to take the previous direction path, you get the answer from there. Whichever are the best case, you actually pop it out. And this tells you what? This tells you the operations, or the minimum operations to be that case, required to make Si and Sj equal. And this is the caller function basically you can get for S1 and Sn. Now what do you get? Let's say you call this caller function, you pass S1 and Sn, and out pops up C, or let's say out pops up O. O means that how many operations do I want for S1 and Sn to become equal. Now you must have those number of operations left with you, right? That is why I passed K. You have a K variable that is maintained over here. In the initial function calls that we did inside, you never utilized this K because you always skipped the elements that you were talking about. But right now when you're considering those elements and trying to make them equal, this O should be less than equal to K. If it is, then what I can do is I can call another function and I can say, okay, ith letter has been used, so move I plus 1. Jth letter also was used, so move j minus 1. Keep s as same because I want to pass the string for utility purpose. And now how much k decreases? K decreases and becomes k minus o. And added to that, your answer has incremented by 2. Why 2? Because you have actually used up 2 letters and made them part of a subsequence. So your overall largest palindromic subsequence has incremented its length by a 2 size. And this is the main idea. I hope this should make sense. So what is going to be our pseudo code in this? We'll say that there is, let's say this function call that I had at the top passes I, okay, passes j, passes s, passes k. Inside this, what do I want? I want, okay, first of all, the base cases. If I crosses j, I want to return a 0. Because if I has crossed j, then I know nothing is going to happen. I comes from left, j comes from right. Then if I has crossed j, oh, this is a problem. If I becomes equal to j, that is they both land at the same character. If you have the same letter that you land at, you basically return 1 because a single letter is palindromic in itself and there is nothing more that you want to convert it to because single letters mean there is 0 operations utilized. This is return 1. 1 overhead indicates that 1 length got added. And now you can have options. Option 1 can be, had you called the function without considering the ith letter, so I plus 1, j, s and k. Option 2 can be, had you called the function without considering the jth letter, so this is like I, j minus 1, s and k. And option 3 is, before you go to option 3, basically you can say like option 3 is over here, and then I first get c or o whatever, that is by calling that particular difference helper function. I get those c value, and if I feel that like c value is less than equal to k or o value, whatever that was, I just took a variable naming for pseudo structure. If c is less than equal to k, option 3 can be function considered I plus 1 letter, consider jth letter also, sorry, consider ith letter, consider jth letter, so I plus 1, j minus 1, s and k decreases with c. And now of course, I have like in this operation, this is plus 2 also because 2 length got increased. So now what is the answer? Answer is max of OP1, OP2 and OP3. This is the pseudo structure. Now, where does DP come into picture? You might think that this is a recursive based idea just to maintain the states that we're talking about. I, by the way, tried to make a lot of clear part. Where am I getting this intuition from? You had multiple answers to check. You had enough time complexity to explore, and you were looking for palindromic size, hence I and j state to be maintained. So once this part is clear, the next part comes is, where is DP into this? The DP comes because this solution is not going to still work in terms of not giving you the right answer, but rather this would run in TLE. Why does this run in TLE? Because you haven't actually made sure that you reutilize your states, correct? You're passing states as I, you're passing states as j, and you're passing states as k. So I, j and k, because s over here is constant, I, k, j and k are changing all the time. So their answers are getting reutilized. If their answers are getting reutilized, I need to make sure that I don't use excessive calculations. That means now I would want to do something called as memonization at this location, memonization at this part. And this is why DP is what I started off as an idea. DP basically means like DP is one of the DPs that we normally write is called recursive plus memoized solution. So this is one of those particular solutions. So now what I would simply want to do is somewhere over here in the piece of structure code, I would have that, okay, DP of, you can say I of j of k, if it's not equal to -1, that means this answer is there with me. If this answer is there with me, why do I want to calculate all of this again? No, let me return this answer directly, and else just store this max answer in dp of I of j of k. Okay, and this is my overall pseudocode, and I hope this should make sense. You can give it a 2-minute thought again. Again, not a very beginner friendly problem. You should have I should say basics of recursion clear so that you're able to understand states, and then memorization also clear. But then this is expected. This is a medium level problem in Leetcode. So up to medium level, DP or this sort of DP, which is, I should say, very classical recursive memorized DP, is frequently visible. Okay, let's look into our code piece and we'll understand how do we implement this out. Okay, so I have a DP. I have declared this globally. Now I have the sizes as 201, 201, 201. Why 200? Because I had 200 length of S. So I can basically have 200 max plus 1 just to have a 1 base indexing, extra those index that I want. So 201, 201. So this is like I maintenance, J maintenance, and then K's maintenance. Now K's maintenance is again in 201 because you cannot actually go more than 200, that is given on K. Great. Now I have this distance helper function. You can see very clearly. If I pass a character A and B, I get their absolute difference, that is like D, and then I pass the minimum of, or return the minimum of D and 26 minus D, or that D1 and D2 that we're talking about. Now let's look over here first. In the caller function, you first memorize this DP with all negative ones. You have n equals to size. Then you call this solve DP function. You pass the string 0, that means I, n minus 1, that means J. So the first and last indexes, and K as it is. Now when you go inside this, you have something called as I greater than j, that's the base case, return 0. I is equal to j, return 1. Now if dp of I of j of r is not -1, return that as only. So I of j of r, sorry, I've passed r over here, just variable convention, you can just mark anything. And then when I say I have the answers that have the options, basically, so I have an answer variable. So this is option 1. Option 1 is pass or like remove ith letter, don't consider that, jump basically. So that's I plus 1, j, and r is that is it. Answer gets maximized with the other option, that is, had you been ignoring the jth letter, so you go to j minus 1, and I is as it is, r is as it is. And then you first figure out the distance between si and sj. Had you want to convert si and sj equal, if the c value is less than equal to r, then I know I have enough r for that. So answer gets maximized again with what is option 3. Option 3 is 2 plus. Why 2? Because 2 means you have added 2 letters in a subsequence, so length gets 2'd. You can say incremented by 2, sorry, and then you call this function again, I plus 1, j minus 1, and r minus c. And then this answer is max stored again back in ijr so that it's memorized, and then you can return it. Okay, so I hope this part should be clear. This is a very neat and simple DP structure, and I think that is all that is there in this problem. Now, what about the time complexity that we are looking over here? We are, of course, looking for a time complexity that works like this. So you have a DP that is maintained and has states as 200, 200, and 200, and everything is memorized basically. So there's a very short form of writing this whole idea, that this helper function being constant, roughly you can say that your DP solution is working in, like you can write a time complexity over here. Time complexity is O of 200 cube. Okay, and this 200 cube is going to work. Why? Because as we expected, this is less than 10 power a dot. What is space complexity? It is also O of 200 cube, because you basically had this DP that had been initialized and used for a 200 into 200 into 200 size. Okay, so I hope this problem is clear. Let us quickly move on to our third problem. All right, so sum of k subarrays with length at least m. You are given an integer array nums and 2 integers k and m. Return the maximum sum of k non-overlapping subarrays of nums where each subarray has length at least m. Okay, let us quickly generalize this problem. Now, it has been said that you have an array given to you. That array has numbers and size. You can say array looks like this. A equals to A1, A2, A3, A4, so on till AN. Great. Now, you have two variables, K and M. K and M. What do they represent? You are basically looking for K subarrays. Those subarrays should be non-overlapping, and they should have at least m size. That means if let's say m is 2 and let's say k is for example 4, that means you're looking for 4 subarrays which do not overlap and those subarrays should have at least a length greater than equal to 2. So what I can do roughly over here is something like this. Let's say I pick up the first subarray of 2 length only. This is one subarray created. Now let's say the next subarray can start from here also, because it's not necessary I want to consider every element. Maybe I can skip A3. I can be like, okay, from A4, let's consider, and this subarray I'll create of 3 size. Why? Because 3 is greater than equal to 2. Then let's say I create even another subarray of, let's say, 4 size, and so on. And I do this, and let's say I create one more subarray of, let's say, 2 size. Roughly like this, I think we can extend my AN over here. Now when I do this, I end up with 4 subarrays. They are not overlapping. See, you are not overlapping them because A1 to A2, this is like one, you can say, window over here. This is another window, this is another window. So they are not overlapping. They are 4 subarrays, and they have at least 2 size. This is like of 2 size, this is 3 size, this is 4 size, this is 2 size, and every size is greater than equal to 2. Great. I hope this makes sense. So now when I do this for all possibilities that is there, what is my final target? My final target is to find the sum of these arrays. Let's say I pick up this array, this array, this array, all these 4 arrays that I marked off with, they will get you some sum. This will be like S1 sum, S2 sum, S3 sum, S4 sum. Use summation all of them. So like summation of S1, S2, S3, S4. When this happens, you basically end up with a bigger sum, a capital S value. This capital S is coming from figuring out 4 subarrays where every subarray has at least M size. Now when you get this S value that you finally have, you want to print this. But this S value can change. There are a lot of possibilities. You could have taken any 4 subarrays which are non-overlapping and they had at least M size. Of course, if you made sure, this S could have been changed. This S could have been something different. You want to print out of all such permutation and combination this S guy, which is the largest one possible. Let's go back. Read the statement. Maximum sum of k non-overlapping subarrays of nums where each subarray has at least of M length. Okay, now let us look at the example 1, 2, -1, 3, 3, 4. Let's take it over here. So 1, 2, -1, 3, 3, 4. And what is k and m? K is given 2, m is given 2. Okay, so k is 2, m is 2. Now you want 2 subarray of at least 2 size. I can pick one as this, other subarray can be this. Both of them have the right conditions. This is of 2 size, this is of 3 size. So both have size at least 2. What is the sum coming from here? This is 3. Sum coming from here is actually, I think, 3 plus 3 plus 4. This gives you 10. What is the overall sum? This is 13. And what do you print? You print 13. Argument is anything better than 13 is not possible. And this is the answer. I got 2 subarrays. Every subarray was at least m length. And the maximum sum I created out of accumulating everything was 13. Let's see the next answer. -10, 3, -1, and 2. Okay, so what we can do over here? You have -10, 3, -1, and -2. I think this is the case. Yes. And k is 4, m is 1. K is 4, m is 1. So you want 4 subarrays. Now in this case, you basically are at the question's will. You had 4 subarrays to create, and the least size you can actually create for any subarray is 1. So you can take this subarray, this subarray, this subarray, and this subarray. You have 4 subarrays. Every size is greater than equal to 1. To be specific, every size is exactly 1. And what do you get? The overall value, -10 plus 3 minus 1 minus 2. This is actually -10 only. And what's the answer? Answer is -10. Okay, so I hope this part is clear. Takeaway from this particular question right now as you read along should be one important thing, that is elements can be skipped. Don't think that you basically are looking to capture every element in a subarray. That's not the case. You're trying to figure out k subarrays. They should be non-overlapping. So in between them, elements can be skipped. Elements might not be considered. That is a possibility. You saw over here, -1 was never considered. And it can also happen that you actually have to consider everything. So you have to take botheration about every particular case. Okay, I hope this is clear. I hope the question part is clear. Let's move on to our intuition. So first intuition that builds up is from time complexity. Let's look at n and k and everything else. M is very small. It's like 1 to 3. So I'm not talking about m right now. But if you look at nums and we look at k, basically both are given in 10 power 3 order. This is like 2000. And then this is like roughly saying k is like, let's say m is 1 in this case. For example, if m is 1, then k becomes 2000 also. Floor of nums.length by m. So this is 2000 again. So that's like a 10 power 3 order. So I have, if like I talk about a 10 power 3 order to be created of any solution, I can work with solutions that are like O of 10 power 3 also. But I can even create a solution that works in O of 10 power 3 power cube, as in O of 10 power 6. You can work with 10 power 6 also, right? Because 10 power 6 is lesser than equal to 10 power 8, or in this case less than 10 power 8. So if you can work with a 10 power 6 based solution, what does this hint you? If you look at n, if you look at k, if you create something like n into k, if n is also 2000 and if k is also 2000, you will actually end up creating a solution that is like 4 into 10 power 6 order, which is going to work. So that means solution like this is promoted, solution like this can be made. And this is a very good hint to start off with. You basically have a solution that can be done in n into k order, which means if you run like 2 loops, one is n, one is k, that is fine. That is absolutely fine for you to do so. This is idea 1. This is expected time complexity. I hope this helps. I think you can pause the video now and from here try to begin one small idea in your head that, okay, how do I get a solution that works in n into k order? Alright, now let us move on to our next thing. Let's first analyze that what is exactly asked. I'll generalize the whole idea and let's see what happens. Let's say you start considering the elements from I equals to 0. It goes on, and you land at a random I value. Now when you are at random I value, what are you trying to look for is, for this random I value that I finally landed at, I'm assuming that everything before that is already been considered and whatever you wanted to make has already been done. As in, let's say you wanted to make, let's say J subarrays. It's already done. You have created J subarrays. You wanted to create J minus 1 subarrays. It has already been done. The best answers possible for all particular permutation and combination for you have already been stored. When you are landing at this ith index, you can imagine that should I use this ith index? That's the first question. Or should I not use this ith index? I can be like, okay, one possibility is maybe I don't use this ith index. Maybe I can just say that, okay, a of I is something I don't want to use right now. So whatever is my like subarrays that I was trying to consider, this I element never pops up. Fine, that's also great. This is one possibility. So like I can write an option 1. Option 1 is never bother with a of I. And what is the other possibility? The other possibility is actually start bothering with a of I. You're like, okay, I want to consider a of I. Now, how do you consider this? The best way over here can be a very simple idea. You can say that if I say I've considered a of I, that basically means I am trying to make sure that a subarray ends at this location. Any subarray that I have ends at the a of I element. Now, if a subarray ends at a of I, that basically means there would be a start of that subarray. Let's say this is the ending part. Let's say this is E, where it ends. So there would be some start, right, between which this subarray falls. And remember, the condition is that this length should be greater than equal to M. So tell me, if this length should be greater than equal to M, you think you can create a subarray that looks like this also? If you extend this a little bit more, like this, is that fine? Because you want greater than equal to M, right? So an exactly M size subarray, M plus 1 size subarray, M plus 2 size subarray, M plus 3 size subarray, M plus 4 size subarray, so on till the back, everything is possible to create. So if A of I is the last guy where I make sure an subarray ends, then from that ith place, if I do I minus M, then all the indexes from, you can say 1 to I minus M are valid to be taken as a start of the subarray I wanted where ith element is ending or is the end guy. And this is what creates a solution that brings up possibilities into picture. And when possibilities come into picture, we just saw the second problem also. When you look for a lot of possibilities, when you look for a lot of cases where everything has to be explored, you basically look in some sort of a solution which is DP based. Okay, and this is why I'm going to write a DP based solution. I will try to come up with some states based on this initial idea that we discussed, and I hope this helps. Again, this is not a very beginner friendly problem. You need to have a little prerequisite of DP to understand states and everything. So if you're not familiar with that, I would highly suggest to you that for Leetcode Contest, try to practice basic DPs, tick off everything that is medium in DP in Leetcode and practice that. I think you will get a hang of these states and all the other, you can say, greedy part that I'm talking about in this. Okay, let's go. So I have all the possibilities that I want to check. So I'll define a DP. I'll say, okay, DP of I of J is equal to, had I considered elements till ith index and want or wants to make for j subarrays, what is the best answer? This means from, let's say I'm using a 1 base indexing by the way, so I'll say from 1 to the index I, if everything has been considered by you and you have made j subarrays totally, what is your best answer? BA, best answer. This is going to get stored in dp of I of j. I hope this makes sense. Now, how do I make sure that states transit? How do I make sure that transition happens? I'll say that dp of I of j comes up from two options. What is option 1? Go back to the initial idea. If you are currently at the ith element and you never want that, okay, I am trying to take this element into picture, then you can basically say this is dp of, don't take the ith element. So whatever numbers did you consider till I minus 1, that, and because you're still looking for j subarrays, right? So j. This means whatever answer was stored for elements considered till I minus 1th index and j subarrays were created by you, like you had created j subarrays, get the answer from there. This is option 1. This says ignore a of I. What is option 2? Option 2 is, okay, I am going to consider ith element and then I'm going to make sure that that ith element is the last guy in a subarray that I've created, the jth subarray you can say that I've created. If that is the last guy of that jth subarray that I'm creating, I need to make sure that I have something like dp of j minus 1. J minus 1 should be clear. Why j minus 1? Because this jth subarray is what you created right now. So this jth subarray's last guy is I index. But who is the start guy? What do you put over here? What do you put at this place? This guy should be the best possible guy you could have taken from, why did I say best possible guy? From the options that you had of all the possible starts. Meaning, you could have stored a value at this location. That is like some dp of I of j would have been at this location. Some dp of I of j would have been in this location, this location, this location, this location. Not dp of I of j, rather dp of, you can say dp of I minus, if this is like I, so you can say I minus m, j minus 1. This is also there. I minus m minus 1, j minus 1. This is also there. I minus 1, I minus m minus 2 of j minus 1. This is also there. So all the previous guys which can be considered a start, this place, this place, this place, this place, I need the best out of them. And let's say the best out of them is over here. Let's say the best guy is over here. This is like s dash, this is the best guy. So this has a length at least m, because I know I am taking that window size to be greater than or equal to m. And now I would say whatever is the answer calculated till this much portion, take that, add to that, how much? Add to that this subarray's sum. And this is where you can also implement a more important idea, is how do you get this subarray sum? Advanced idea again, pause the video and think to yourself, how do you actually get a subarray sum quickly in CP logic? There is something called as prefix sums. I could have, of course, done a brute force over here, but then that is something I don't want because I would be going unnecessarily with a very high time complexity. I'm just looking to create some subarray sum which I can figure out in a constant time period. So I know there is sort of a start position, there is sort of an end position with me. So why not create a prefix sum array on this whole subarray, and I would just take out whatever is the sum till here, like till E, the sum till s minus 1, like the s minus 1, and that basically lands up this orange portion, that is the middle subarray. So the idea would be that have I considered the ith number to be a guy on which the jth subarray ends, then I would want that dp of I minus m is considered, okay, and plus what is considered dp of I minus m, then what is considered prefix of I minus prefix of I minus m, this is considered. And then this thing that I did, it is for I minus m. I would want to do this for I minus m minus 1. I would want to do this for I minus m minus 2 and so on till something like I minus you can say something like an offset like O is greater than equal to 0, or like something like offset is greater than equal to 0. So all the possibilities that go back. So to do that, I can maintain some sort of a best offset that I had initially, a global sort of a variable, which always maintains this guy for me, always maintains which is that best overall, like you can say dp of I minus 1's all possibilities that I had minus 1, I minus I minus m minus 1, I minus m minus 2 and so on. I can maintain this with me, and every time I want to update dp of I of j, I can use this first option, that is never bother with a of I. And if I use the second option can come from simply getting prefix of I and then plus that best offset that I have. Okay, best offset would basically mean what is the best offset that is this orange portion, Okay, orange portion is dp of I minus m of j minus 1 minus prefix of I minus m, and this I minus m minus m is always the best guy that is there, because you would be maintaining sort of a looping structure, so you would be always getting the best offset. Okay, I hope this part should make sense. Pause the video. I'll show you, of course, the implementation. From there, I think this should be much more clear, because right now, I think for all the beginners out there, you must be thinking that I told you that you want to take all the options from the the best start that you can start off with. Like, let's say this is S, which is exactly has a size of m, then you want m plus 1, m plus 2, m plus 3. So why am I not running another loop to figure out m plus 1, m plus 2, m plus 3? That is again futile. The other thing is, if you can somehow, like if you are basically wondering what answer do I want to get, if for this much region, that is this much portion, if you can already get the best offset, then don't you think this best offset and this prefix of I over here will effectively make your answer? Because best offset stores the dp value also and minus that the prefix value also. And then if you get prefix of I and then this is the best offset, so the equation overall would actually turn up as dp of I minus m of j minus 1 plus prefix of I minus prefix of I minus m. Okay, I hope this is clear. Let us quickly jump to our coding logic and we will see how do we implement this out. Okay, so this is my code. What we'll do is we have a global dp, I have a vector of long, n size is taken, then I have a prefix array that I created. Because I'm doing everything in one base indexing, it was very easy to do that. So I'll have n plus 1 size, everything is initially 0 or 0 ll because I have long. I run a loop from 1 to less than equal to n, prefix of I becomes its previous guy plus nums of I minus 1. This construction part should be very clear. Let me quickly iterate over here. Prefix of I basically means, like, let's say the sum like array is, let's say 1, 2, 3 and 5 for example. So prefix should look like 1, 3, then 6 and then 11. So how do you get this? Sum till here plus sum till here plus sum till here plus sum till here. This is what you want to do. That would effectively mean that you get the first element that is directly mapped, and then second onwards the previous guy plus the guy that is there in the array. So this is like an array, this is like the prefix. Okay, this is what I'm doing. Prefix of I is prefix of I minus 1 plus nums of I minus 1. Why I minus 1? Because nums actually runs in 0 based indexing. So you are running index on 1 to n. You want 0 to n minus 1 to run in this. Now you have the dp. Resize it to what sort of a state that you're overall trying to maintain. You're trying to maintain n and you're trying to maintain k. So I'll say n and k. Now what will I do? First of all, I need to have the base cases sorted. What is the base case? Let's go back into dp and I think let's do a little more discussion on this. What are the base cases in this? If you talk about dp of I of 0, that means you have considered elements till I, but you did not make any subarray. Now, if you made no subarray, then tell me what is the sum? What is the best answer? Best answer is 0, right? So for all I from 1 to n for that matter, or let's say for 0 to n for that matter, should be declared with this value. This is the base case. And by the way, what is the answer? I think we did not discuss this. Answer is very simple. dp of n of k, which would mean that have you considered all the n elements and you exactly made k subarrays. By the way, also making sure that every subarray had at least m size, because you have windows that you were having. So you know that this is what you finally want to return. Okay, now let's go back to the code. We'll say this is our base casing. dp of I of 0 turns to be 0 for everything from 0 to n. and then initially everything was int min. So now I have the best things that are saved. Now what I can do is I can run a loop. Right now I'll try to make number of arrays. So I'll say number of subarrays I made is 1, 2, 3, 4, so on till k. Then inside that loop, I have the offset value. This is int min. Now see, this is global. Why do I say this is global? It's not global like it's outside the function, but it's global in the order that in this for loop, this is never, you can say, redeclared from int min again. This always is maintained and you can say replaced with the best answer till that location. So you can say that now I have dp of I of j. What is that value? This is option 1. So you can say this is option 1. Option 1 is direct. dp of I of j becomes dp of I minus 1 of j. That is never bothered with a of I. Now if I did not bother with a of I, this is the direct answer. How do I get the option 2? For option 2 I need a m window or at least m window. So I know I'm not going to directly write option 2. Option 2 can be written if I minus m is greater than or equal to 0. If I minus 1 is greater than or equal to 0, then I know I have an m size window that is now available with me. So starting off with m sized windows, I'll say best offset gets replaced with the best answers. That is max of best offset, that same variable again, and dp of I minus 1 of j minus 1. Why I minus m and j minus 1? J minus 1 signifies that j minus 1 subarrays were already made. So you're trying to make the jth subarray. I minus 1 indicates that start location. So the best answer saved for dp of I minus m j minus 1 minus prefix of I minus m. This is like the prefix of, you can say over here that we discussed, prefix of L that we were talking about, or rather, sorry, not L, prefix of L minus 1 that we were talking about. This is the guy over here. Okay. And then once you get this best offset, when you come out of this if check, you can just make sure that dp of I of j again gets maximized with prefix of I plus offset. Now you don't get confused. Like many of you might think prefix summation looks like prefix of r minus prefix of l. Why is this not negative sign? This is not negative sign because this doesn't signify prefix of I minus something. This basically signifies if you replace this, let's say best offset is replaced with this value. If you replace this value over here, don't you think automatically you have prefix of something like r minus prefix of l, and then this is the best answer. Okay, so that is why this is the equation substitution that we have done. So don't get confused. This would definitely be a plus symbol. Okay, again, pointing out small things I feel might be very confusing for a beginner. And once I do this, now remember, what does this do? You might be thinking, I'm not doing something like this. I'm not basically standing at some S location and I'm going back to get the best answer. It's not required because you are maintaining a global offset outside the for loop. So once this loop extends from 1 to n, and as soon as you start getting m sized windows, you always store the best answers. So let's say you reach up a random window size and let's say you're at ith location. At that location, whatever is that best offset that you have finally initialized and stored and whatever you can call that best offset considers everything possible. It doesn't consider this S guy, it considers S minus 1 also, S minus 2 also, S minus 3 also, right up to 0. That means you don't need to find this best offset again and again because this got globally initialized. Okay, and this is why this idea works. Now dp of I of j is, as I expected, becomes again this maxed out value, and then when you end this for loop, this for loop, for example, in a for loop, you can say that you have correctly made the answers possible for one subarray. Then you will do this for 2 subarrays, 3 subarrays, 4 subarrays, and when you end this for logic, you have correctly considered all elements and you have made all possible answers till k value. So now dp of n of k will give you the right answer. Okay, I hope this is clear. This requires a lot of understanding of prefix sums and dp because prefix sums help us get answers quickly from a range to range. If I would have not done that, I would again have to find this orange windows subarray sum because I'm looking for a sum that I had in this case, and I just did prefix summing so that it helps me better that time complexity. And now remember, in an expected time complexity discussion, we discussed what sort of a time complexity can you actually go to. Let's discuss over here. If we have an n order over here to take the prefix sum, this is n order here for the base cases. What is this? This is like k order. Then inside this is pretty much constant. This is n order, and then this is also pretty much constant. So don't you think you have actually ended up with a time complexity that looks like O of n into k, which is O of 2000 cube. Sorry, not cube, square. And what about space complexity? Again, n into k, which is O of 2000 square. Okay, there is extra space from the prefix array also, but let's not consider that. It's the lower part. Now, why did the expected time complexity help us? because I had already an idea that I was looking to create an n into k solution. And that is what promoted me or motivated me to create a DP. Now, this might not come off very intuitive if you're very beginner in this. But for all those who can relate with me, once you look at constraints and you figure out that, okay, some state maintenance is something you want to do, and you as soon see constraints that are in 10 part 3, 10 part 2 order, you actually start looking for DP. Because then if constraints are in this limit, it indicates that a DP solution must be promoted, since the second thing was, of course, you wanted all possibilities. So this ends up our problem, and I hope this part should be clear. You can now again try to dry run this out, but I don't think that is going to be very good because DP is a 2D DP. Just to dry run this out, you will run a 2D DP in your head. For smaller cases, maybe you can do this with a pen and copy, but I think for any medium level coder, this direct method of understanding DP should be more important. You should understand states, and that is the main practice that we want to build over here. And this is the code and problem solution for 3. Okay, let us move on to our problem 4. Lexicographically smallest generated string. You are given two strings str1, str2 of length n and m respectively. A word of length n plus m minus 1 is generated to be string 1 and string 2. Sorry, generated by rather string 1 and string 2 if it satisfies the following condition for each and every index. If str1 is t, that means the substring of the word of size m starting at index I is equal to str2. That is word of I2, I plus m minus 1 is equal to str2. And if str1 is of I is f, that is, you can say like true and false terminology, the substring of word of size m starting at index I is not equal to str2. Return the lexicographically smallest string that can be generated with str1 and str2. If nothing can be done in that manner, then you return an empty string. Alright, so this has like a lot of terms that we want to discuss. Let's do this quickly. So what are they saying is, they will say that there is an str1 string of n size. So you can see the letters are there like s1, s2, s3, so on till sn. And then there is like an str2 string of m size. Letters are again like s1, s2, so on till sm. Now str1 indicates true and false. It indicates only letters t and f. You are trying to come up with a word. You are trying to come up with a word that you want to return. This is again a string. And then this construction of word is dependent on str1 and str2. How? You basically start iterating on str1. You'll be like, okay, let's go to every letter. Let's say the letter turns out as a T. If this letter turns out as a T, then that means I want that in the word from this index onwards, str2 fully is found as a substring. That means you can say from like here to here, it is str2. And else, if I say that this is actually a false, then I want that from that particular index in the word, I want that this is not str2. And this is the T and F nature that I'm going to have. Now, when I actually complete the iteration from left to right on this str1, and I've executed or made my word accordingly for TNF, 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 I will come up with some word string. I want to return this word, and I also want to make sure that this word is lexicographically the lowest. This is my target. Okay, now what is lexicographical manner? For all those amateur people and beginner people, lexicographically simply means a dictionary. If you say that a string A is less than B, then you're basically saying A comes before then B in a dictionary. In CP logic, what do we say? If A is less than B, then the first place from the left where a letter AI and that same position letter BI don't match, let's say this is not equal, the first mismatch that happens from the left hand side, if AI is lesser than BI, then I'll say A is less than B. So this is how a dictionary works also, by the way, that the first mismatch that happens, the letters which have smaller come overall as that word before then the other word. So this is what happens. This is called lexicographical order. So I want a word which is lexicographically lowest out of all such possible permutation and combinations that I could have made with following my rules right to the book, that T comes, str2 should be there, F comes, str2 should not be there. Great. Now let's us see the test cases, and I think this is going to be much more clear. Let's take this case, TF, TF and AB. Okay, so you have TF, TF and then AB. Now first is T, which means AB should come as a substring. So you like A and B. Now the next is F. If next is F, I don't want from this location onward, this position, this like overall window that I've created of 2 sides. Why 2 sides? Because 2 is the substring that I'm talking about, should not be equal to AB. So I can place an A over here, and now I know this much portion is not equal to AB. This is BA, BA is not equal to AB. Now a T comes, I can place a B over here, C. Now the next substring of 2 sides is equal to AB. So T follows, then get an F. Okay, place an A over here. This doesn't follow. Okay, now you can see the last 2 letters. This of course is creating a substring of 2 sides, which is not equal to AB. Now this is actually the best answer. Why do I feel this is the best answer? Because remember, multiple answers were possible since you were talking about lexicographically lowest. And why did that happen? Let's talk about a small case over here. Let's see the last 2 places, BA. Now, all that is the question telling you is these last 2 places should not match with AB. So if I would have made this A letter as, let's say, Z, don't you think this would also be satisfying everything? See the first 2 places matches true. Next 2 places don't match false. Next 2 places matches true. Next 2 places don't match false. So this follows the pattern, right? But compared to our original answer A, B, A, B, A, which is better? A, B, A, B, A and A, B, A, B, Z, for example, this string is lower. If I call this capital A and I call this capital B, then A is actually lower than B lexicographically. That means you can now understand there were possibilities that you wanted to explore. And on all those possibilities, that is why we said we want the lexicographically smallest order, because if you don't put that, then any or multiple answers are possible. We don't want that. We want that one perfect guy, which is the best string possible. And hence A will be preferred, and this capital A as A, B, A, B, A was given as an answer. Let's go back. Yes, that was the case. Okay, I hope this is clear. Let's go example 2. Over here, they have actually said no string satisfies the condition. You can pause the video, try to do this. You might actually find up seeing that nothing is possible. And over here, again, same thing. You wanted an F, that is initially it should not match, and string 2 was D. Great. You can just place a single A. A doesn't match D, does it? No, it doesn't match D. So I know I am good to go. Okay, and this is the whole question. Now, the next thing to observe is, by the way, that once we have understood the cases and the question, N and M are not very large. N is 10 power 4, so this is a large number, but M is not large. This is 500. So what does this tell me? Let's talk about the complexities that are allowed. If N goes in 10 power 4 order and M goes in 10 power 2 order roughly, then can you create an N into M solution? It's possible. Yes, it's possible. You can create a 10 power 6 ordered solution in this case, which would be less than 10 power 8. And this is like a good starting point. Now, if N into M is possible, that means 2 for loops are possible. I can have a for loop that runs on N. I can have a for loop that runs on M. I hope this should make sense. Now, this is a very important discussion. You can name this as expected time complexity. And this tells me that, okay, 2 for loops are good to go. Maybe you create a solution that talks about working with every substring, and that's still going to work. And this is my first starting point. You can say substrings can be worked on. What does this mean exactly? Of course, as we progress, you will understand this idea. I'll just write it over as substrings can be worked on. Now, let's talk about the main idea. Now, if substrings can be worked on, my argument is we can have a very simple simulative based approach in this because the time complexity allows. You don't need any smart tactics to do or solve this problem. Because the complexities were allowed, even though it looks like a hard problem, we can make this a very simple, intuitive and simulative problem. What can I do is, I can say that, let's say I have the word string that I'm trying to create. First of all, this part should be clear. What is the length of the word that is going to have when I actually make the word? If I return an empty string, that's fine. But if I actually end up making a right word and I want to return it, what do you think is the length of this word? You have n size of str1. You have m size of str2. you're basically looking that str2 comes how many times? str2 comes exactly n times. So let's say this is 3. Let's say there's 3 sides. So 3, 3, 3, 3. This is what you want. So on, so on. How many times? N times. So this formula basically becomes n plus m minus 1. How does this come? You can quickly observe this over there. Like you can say this is that first green window of m. And then all these small places are like one lengthed. So this is like 1, 1, 1, 1. So n plus m. And then minus 1 why? Because these ones are going to extend only n minus 1 times. So m plus n minus 1 or n plus m minus 1, whatever you write that, is going to be the word length if you had been able to create this word. Else, of course, you're returning an empty string. Okay, this is clear. Let us work with an example now. Okay, so we have understood the length that we are trying to create, n plus m minus 1. So let's say I have a string 1 that is tfff and then string 2 that is aa. Let me simulate. What I'll say is, right now, the word is created of how much length? This is like 3 length and this is 6 length. So I'll do something like 6 plus 3 minus 1. So that is 9 minus 1, that is 8. So 1, 2, 3, 4, 5, 6, 7, 8. Right now, nothing has been filled. So I'll say these are free positions. If I say they are free positions, I can mark them with some particular character for myself so that I'm able to identify they are free positions. Let's say 1, 1, 1, 1, 1, 1, 1. These are free positions. Now what will I do in the first iteration? I'll say, first I want to make sure that wherever a t falls, I do find an AAA from that word onward. So let's run a for loop, and in that for loop, first fix all t's. That means I'll run a for loop. I'll go to, you can say, I'll go to the first letter. This is t. So if this is t, that means from this position onward, I want an AA. So I'll do that. I'll say this becomes A, and A. Now added to this, I need one more data. That is, imagine that because now AAA is there at these locations, don't you think because of this t value, they have been fixed there? Do you want them to change? Do you want AAA to become something else? No, that is something you don't want, because when you have explored the t, that t tells you that from here onward, I want a triple A. I don't want anything like that. So I can have some sort of a fixed array also, which is like a Boolean array. Let's say it is initially having the same size. Let's say 8 size over here. Everything initially was 0, which told that, okay, this was not fixed. But now that I have fixed the first 3 locations, I'll say 1, 1, 1. These have also now become fixed. I hope this is clear. Now we'll move on. We'll say, okay, went to a F. This is an F. I don't want an F. I'm not looking for F right now. Went to another F, no problem. Another F, no problem. Oh, this is a T. That means from this position onward, I want a AAA. So what is that location? So which is that location? This is from here. So I'll say, okay, let's fix up 3 A's. Okay, this is like A, and these 3 numbers become 1, 1, 1. These are now fixed. And this is when you come to the last F and you have explored everything. So now you have landed up with a string after the first pseudo structure, first pseudo code that you have done. That is, you have explored everything that was T. You have AAA 1, AAA 1. 1 signifies that that position is right now free. I have not allotted any character there. And other places which are filled right now, they are filled only because of the str1 that I was talking about. Great. Now, after this, what I can do? After this, I can do the same thing for F. But before I do this for F, I need to make sure one important thing. You now need no free characters. See, the free characters right now are at this location and this location. Before you explore F, you need to fill them with some letter. You need to make sure that when you make a looping of F, what is this particular character going to be? Now remember, in the question, it was clearly mentioned you want lexicographically lowest string if possible. So these all positions are fixed. These are fixed. These are free. These are in your hand. Now, if it's in your hand, tell me, what's the clever idea? What is the lowest letter I should place at this location so that I'm lexicographically better in always situation? I know I should place an A, which means I will again place an A over here, and this is to my free will. So I'll not say that these A's are fixed. That means I'll not convert this 0 to 1. Fixed means that they are fixed by nature because of T. But right now, I haven't fixed them because of T. They are on my will. I said that I'm making them A because I knew that lexicographically A was better. A is always the lowest character. Nothing below A is there. So let's fix them as A. So my first logic is with all the T's. Second logic is all free letters become A. Great. And then the third logic, do this for all F's. When we do this for all F's, see what is going to happen. Look at the idea. You start running and you go to this T. This is T, so no worries. Go to F. Oh, this is an F. That means this much part should not match with str2. And the problem is this is matching. You made the lexicographical best choice, but now AAA matches with AAA. You don't want that. So now you want to, of course, change some letter in this. The argument is, which letter should you change? This argument, first of all, has two questions. Do you want to change a letter from the left side or the right side? First, ask yourself this. I, of course, want to change the letter from the right side. Why? Because if I change from left side, lexicographically, I am making a worse choice. Because when I talk about lexicographical strings, I compare from the left, I go on left, and I find the first mismatch. So if I have to create a mismatch so that AAA doesn't match this AAA anymore, I should do that from the right side, right? Not on the left side. So yes, this should make sense. Greedily, I would try to go on the right side. Now, if I go on the right side, which letter should I change? Should I change those letters which are by nature fixed? Are they fixed? This is fixed 1, which means the T that was somewhere there made sure that these letters don't change. So I will say, let's not work on that letter which is fixed. Let's work on the letter that is not fixed, that was kept by my will. And that is the first letter I find from right. So my next argument after, like when I would do this F logic would be, if I find an F and the strings end up matching, I need to change. So I will say, go from the right, and in that right manner, find the first guy which is actually a 0 in the fixed array. If you find that guy, make sure that that guy changes to something else. Now, what is going to happen over here? If you find this first guy and this is A, and you want this to not match, that means you would want to change this to the next better guy. Now, you have always made sure you're working with A's. Okay, so imagine this works in all cases, by the way. When you are made sure that this is the first guy that is to your will, and it is not fixed, but it matches with the string somewhere, then you can make it to the just next better guy, and just next better guy then A is actually B. So let's keep a B letter over here. And what does this mean now? This means that your free will guy has now changed from A to B, which means now your 3-size window doesn't look exact. This is AAA, this is AAB, doesn't match. Wow, great, good to go. I have done what I wanted. Okay, now let's move on. Let's go to the next F guy. Let's see. Okay, now again I want this 3 window to not match. Oh, it's not matching. Fine, let's go to this F. Oh, it's not matching again. Fine, great. Let's go to this T. Oh, it matches. That's fine. It was a T. No worries. Let's go to F. Oh, this last window again matches. Now this matches with A, and this is F. It should not match. So from the right, find the first free will guy. Free will guy is over here. Let's change that guy to a B. So I'll say this becomes a B. And voila, you have actually come up with the best possible string that could have been there for this test case. Now remember, anywhere while you implement this logic, it can happen that you actually are not able to, for example, you are going from the right. What if you don't find a free will guy? Then you will have to return an empty string. Because if you never find a free will guy from the right hand side, then that free will guy is like you have everything fixed. You cannot change anything. If you cannot change anything and you're still trying to make str2 not equal to that particular window, then how will you change that? It's not possible. That means you will have to return an empty string from there. So all these sub cases can be handled inside a logic only. That this simulation that I'm trying to do should actually end up doing till the very end of the string. If it doesn't, then I'm obviously returning empty string anywhere in between. And then after this also, you have to make sure that, like in this case that I took, it just became a coincidence that you actually ended up with a string that was perfect and it was satisfying all the conditions. What if you actually end up with a string that doesn't satisfy all these conditions, right? It's possible. It's just implementation technique, right? Maybe you implement that inside the code only somewhere in the middle so that you made sure it happens. What I'll show you an implementation of my case would be, I have not taken everything into picture in a single for loop. I'll say that once I end this simulation, I will make sure, because some cases can happen, that this string that I finally end up with also doesn't satisfy TFFFTF. Maybe it happens. So let's make sure again by running one more for loop, like that would be like the fourth part of my code, where I'll again, just for like a checker basis, I'll again check whether the string that I have, word that I have, actually is right or not. whether everywhere that was a T, it is matching with str2, wherever it was not a T, it doesn't match with str2. And if that happens and I am good to go everywhere, then I'll return this word, else I again return empty. So this is like a 4-step based code that I've created, which is going to be very simulative. Now this should be very clear in your mind that this question was not at all hard now if you look at this question in this way. You're just looking to simulate the process. There can be endless implementations for this, right? You can try to maybe do this with some while loop structure, a for loop structure. Maybe you do this in a single for loop, a double for loop, whatever you want. The crude idea should remain same. You want to fix all T's first, then all free A's becomes A. All free positions become A basically, then F's, and then you can basically make this particular check and then in the end return your word, because now if you have passed every check, everything was done and dusted, then this word is absolutely right to return. Okay, and this is my overall idea. This is my overall pseudo. Let us see the code part and how do we implement this. This is my code logic. What I'll do over here is I have this str1. I have this str2. So I'll take out n and m from here. That is n and m. Now I have a result string. What is the size of that? The size is n plus m minus 1. And I've done a very smart thing over here, that is because I had to fill all the free positions later with A. So I've already initialized them with A. If they are already starting with A, later I don't have to initialize them anything. So this idea of filling ones initially, you can just cross off that. It just came to my mind in my pseudo structure, but you can be a little better. You can just fill them with A only in the start. And then you have a fixed boolean, which is n plus m minus 1 size. Everything is initially false because nothing has been declared. So by default values is false in this vector. Now this is my first piece of logic. What do? You go to every size of 0 to n. If it is a T, then from that particular location, you want that particular location, and after that, you actually have a window of, you can say, m size, which is equivalent to every letter in str2, or the str2 basically string only. So how do you implement that? You run a loop from j0 to m, and then I plus j together, it becomes the letter in str2 of j. I plus j, why? Because you basically are talking about windows that are iterating in this particular string. So 3 windows basically you can see over here, but corresponding to that, you're just iterating in 0, 1, 2 always, 0, 1, 2 always. So if this is j, that is 0, 1 and 2, and corresponding there is some I that you had. So I plus j will land you at this particular letter. Then I plus j plus 1 lands you at this particular letter. I plus j plus 2 lands at this particular letter, and so on. So this window continues. You will say res, that is the string, I plus j becomes str2 of j. And then this is fixed because by virtue, a T was forcing me to do that. So this becomes fixed. Okay, just an implementation technique over here. I can just add braces over here so that it becomes neater. Yeah. So this is like my first piece of code. Okay, I can name this like over here 1. Now after this, my second piece of logic. What is that going to happen? Second piece of logic says that now that I've already done, you can say, initialization of free locations with A. So you can say my second piece of logic has basically became my third directly. I've skipped this idea totally because I started everything with A. So now this is my third piece of logic. My third piece of logic says that wherever there is an F, you need to do something. What is that? Go in this string I, string 1I. If that is an F, then have a boolean variable same. First, find whether that M window was equivalent to str2 or not. So for that, run a loop. In that loop, do this, that check whether res of I plus j, that is that letter kept over there in that window, is equivalent to str of j or not. If it's not equivalent, then this is not same. If it's not same, that is, there is a disparity. Okay, break. Now, if it is not same, do you want anything to happen? No, right? Like see over here, when we had this F, this guy F over here, A did not match. So it was fine. You just moved on casually. So you will say if it did not match, then means this same variable would have become 0. So I don't need to do anything. But if it does match, then this is where you need to do something. And what is that code? What is that logic? I explained. You now need to figure out in this window from the right guy, the first place of your free will, which is not fixed, and change it to a B. So you will run a loop from m minus 1 to greater than equal to 0. And you will find is I plus j, that is the fixed guy. Is it not 1? Not 1 means if it is 0, then 0 not will become 1. If it is not 1, then make it a B and break right from there. And this is the best way of how you would make sure that now your, you can say that position has created disparity and now your window doesn't match. Okay, this is my logic 3. Once this ends, now the safety logic, logic number 4, we'll say, okay, let's try to run an logic in the whole string We'll go for same variable. We'll check whether or not it became same, as in is that window having str2 or not. Then outside this code, I'll see if it was t and it is not same, or if it was f and it is same, then these two conditions something I don't want, because if it is t, I want it to be same, and if it is false, I want it to be not same. But if it's t and it's not same, and if it's false and it is same, both conditions will return me an empty string, because I know the word that I created was the lexicographically best word, but that did not also end up being satisfying all conditions. So I need an empty string. I'll return empty. And finally, if this doesn't happen, I return a res. That is my answer that was directly there. Now you can see this runs on every code. You can see this gives me A, B, A, empty, and A that was expected over here. And if I submit this, this gets me a right solution. Okay, so very implementative based question, I should say. And what about the time complexity? You have like an res over here. This creates like an n plus m minus 1 order. Okay, and then this is also that case only. Now you have over here, this is like n order. Then this is like m order. Every time this is n and m only. This is also n and m order. This is also like m order again inside this only. So this is like n order. Then this is like m order. This is one loop of m. This is another loop of m. But both are separated. So you can say n into m plus m. So that is also writing n into m only. This is also n order. This is also m order. So you have actually come up with a solution that runs exactly in the expected time complexity discussion, n into m, which is like a, you can say 10 power 4 into 500. That is like a rough, you can say O of 10 power 6 order solution. Okay. And what about space? Space is going to look like O of n plus m minus 1. That is coming from the string size also and the Boolean vector also. Alright, so I hope this question makes sense. Very implementative based question. And this brings us to the end of our PCD. I hope you like the video. Thank you for watching.